what we do here is go back.
We all know our sun is a star, but what type of star, you ask? Well, it is a main sequence star. Main sequence stars are the stars that are big enough to eventually become a red giant star and are too big to have the lifespan of a smaller red dwarf star. They spend the majority of their stellar lives converting hydrogen into helium through a process which is known as nuclear fusion. And we can further break this process down into a process known as the proton-to-proton chain atomic fusion. This shows us how and what stars are made of, right down to the atoms.
We start off this chain with 4 hydrogen atoms, represented by 4 protons, aka pink glass. We'll split these atoms into 2 pairs, and the hydrogen atoms in these 2 pairs will collide. This is why this process is known as nuclear fusion, because the hydrogen atoms are fusing together. This fusing requires tons of energy and also releases tons of energy. This energy is in the form of light, and as we know it, light is waves, and the waves released by this reaction are gamma rays, as seen in our model as the green glass. Another thing that is released as a result of this reaction is a neutrino as yellow glass, which is what is released as decay from when one particle changes into another type of particle. But the most important thing that is seen as a result of this first fusion is the result of a proton along with the neutron, and we now have 2 sets of these proton-neutron bundles. Because if we remember, the 2 hydrogen pairs we split up each did their own fusion. Now another hydrogen atom will collide with this proton-neutron bundle in another fusion, but this time only releasing a gamma ray. Since nothing's being changed, only another proton has been added to this bunch. This bunch is now one helium-3 atom, which is not really the helium that we know and love, because it still only has 1 neutron compared to the helium we know that has 2. But that's okay, because now our 2 helium-3 atoms can now collide and create a helium-4 atom, and in this collision, it releases 2 hydrogen atoms in the process.
You might be wondering, well, if we need a total of 6 hydrogen atoms to fully do this chain reaction and we end up with 1 helium atom and only 2 hydrogen atoms, wouldn't we run out of hydrogen atoms to collide with? Well, you were correct. That is exactly why main sequence stars live much shorter lives than the smaller red dwarfs. In bigger stars, there is more gravity needed to keep all those particles floating about, meaning that the main sequence stars will have more collision and more fusion than a red dwarf, causing it to run out of hydrogen faster. Once a star runs out of hydrogen, there's no other option but to fuse other elements. 2 heliums, for example, will collide to create a beryllium atom, and if that beryllium atom collides with another helium atom, it creates a nice carbon atom. A bunch of collisions after carbon happens. That creates neon, then oxygen, then silicon, which then turns into iron after some more collisions. This is where bigger stars begin their supernova demise. Every time a new element becomes abundant in a star's core, it begins to push out the previous elements, sort of creating layers, making the star expand and become bigger, to the point where it is now a red supergiant rather than a main sequence star. This type of star requires more gravity to keep those elements in the star. However, iron in the core begins to require so much energy that its energy output no longer balances out the gravitational energy keeping the star in place. This keeps happening until a fraction of a second, the star collapses into a single point and then goes supernova, or a triple B, big beautiful boom in the sky.
Thanks for watching. Yeah, and then you get me fucking punching Eddie off the sun.